All right, guys, welcome to the second part of combination of functions, which is a special type of combination, which is called a composite function. Okay, so let's go ahead and read a definition. So if you are given a function f and a function g, the composite f of g is defined as, so here's some notation. So this is f, there's a little open circle, does not mean multiplication. It basically says f of g of x, which is the same thing as basically saying f of g of x, guys, okay? Which this is a notation that you've seen before, hopefully, just not with a function. Maybe in the past you've seen something like this. So when you see something like that in the past, you'll automatically know, oh, okay, I have a function, and inside of it, I can plug in a 2, so I can evaluate it at 2. So if we're talking about numbers, when you see a number on the inside of the parentheses, you're evaluating at that value, and your result or your output should also be a number. Well, guess what, guys? I know this may look a little bit more complicated, but it's the exact same thing. Is you have a function, but you're evaluating it at another function. So instead of plugging in a number, you are going to plug in an entire function for x, which means that your result should also be a function. Now, one thing to denote about the domain is that the domain of the composite function is going to be whatever is defined for both g of x and f of g of x. So what I mean by that is, first you have to find the domain of what you are going to input. So in this case is g of x, okay? Because that's going to restrict what you can actually input into f. So for example, if the domain of g of x is only from -1 to 1, that means that when you find your result, you can only plug in values from -1 to 1. However, you still need to check that the new function that you generated, it's possible for you to plug in -1 to 1. So let's say that you find out that you can actually not plug in any negatives, so then that restricts your domain even further to say that it goes from 0 to 1, okay? But anyways, let's go ahead and do some examples so that you understand what it is that we're talking about, okay? Let's say that you have given f of x equals x squared, and that g of x is equal to x minus 3. And you are being asked to find f of g of x. Okay, so here's a trick that I typically do. I like to look at this statement here as if there were layers, okay? Notice how I have a couple sets of parentheses, which could be a little intimidating. So what I do is, notice I call this right here the core, and then what's outside, I call that the outer layer. Notice how the outer layer is your f function. So what I do is I go to my f function, which in this case is x squared, and everywhere I see an x, instead of an x, I use a set of parentheses, so I put parentheses square. In my mind, really what I'm reading is x squared, which is what I have. So what I do is, inside the parentheses, I have this function. So what I'm going to do is I'm going to plug in that function inside those parentheses, so that's going to be x minus 3. Now, honestly, that should be your response. If you wanted to multiply this out, you're welcome to do so, but in my opinion, that would be as simple enough, and I would accept that, okay? Now, let's say you want to talk about the domain, okay? Now, notice how it says, this is going to depend on the function that you are inputting. So first of all, the function that I am inputting happens to be the g of x. Now the function of g of x is a linear function whose domain is going to be the set of all real numbers. Therefore, once I do my combination or my composite function, it means that, hey, you can actually use any value. So there's no problem, there's no restrictions. But now let's take a look at this. Now, taking a look at this function separately, this is just a polynomial, and you should know that a polynomial also has a domain of all real numbers. Therefore, the domain for the composite function will end up being all real numbers, because this g of x did not restrict us whatsoever, and because the resulting function was a polynomial. Okay? Let's try b, which would be the same functions, but now let's say we do g of f of x. Notice how this time the outer function is g, so I'm going to start out with this function, and everywhere I see an x, I'm going to write a set of parentheses. So this technically says x minus 3. Okay? Inside the parentheses, I'm going to use whatever it is telling me here to put inside the parentheses, which in our case is the f of x function, which happens to be x squared. So when I simplify this, I mean, you don't have to, but if you rewrite it, it's just going to be x squared minus 3. So once again, if I want to find the domain for this, I'm going to look first at the function that was on the inside, which in this case was f of x. I look at that. The domain is all real numbers, which means it doesn't restrict anything at all for this function. And when I look at this is a quadratic, which is a polynomial, and all polynomials are continuous. Therefore, the domain for this function will happen to be all real numbers as well. Okay? All right, so those are very easy examples. Let's try something a little bit harder. Okay? Let's do a different types of function. Let's say that you are given that f of x is equal to the square root of x. And let's say that g of x is equal to the square root of 2 minus x. Okay? All right, so what I'm going to do is, because I'm going to be doing some combinations, I'm going to find their domains. I'm going to go ahead and find the domain of both of these. Okay? So you should know from the parent function that the domain of the root function is going to be from 0 to infinity, including 0 but not infinity. Okay? And remember, to find the function, so we can use the fact that we know that from here. This values on the inside, so the 2 minus x has to be greater than or equal to 0. That's really what happens. That's the same thing of what this says here. So all I'm going to do is solve for x. So I'm going to say 2 is greater than or equal to x. So in other words, your domain has to be that x is less than or equal to 2. So in other words, your domain is going to be from negative infinity to 2. Including the 2. Okay, we'll keep that in mind later on for what we're doing. Okay, so let's go ahead and try the very first part. So let's say that the first part, you are being asked to find f of g of x. So let's find out, first part, what f of g of x is equal to. So I'm going to go ahead and recognize that my outer layer is f. So for f, I'm going to write down the function, but instead of x, I'm going to put parentheses. Okay, and inside those parentheses, I'm going to plug in the g function, which in this case happens to be the square root of 2 minus x. Okay, all right, this one's a little ugly, so let's kind of clean this up, little algebra. This is technically the square root of 2 minus x. I mean, technically it's not like it's incorrect, but let's just kind of clean up a little bit of notation. One thing to remember before I clean this up so you don't get lost. You should remember that x to the 1/2 is the same thing as the square root of x. So I'm going to use powers here to help me out. So technically what this says, guys, is that I have 2 minus x to the 1/2 power to the 1/2 power. Which means, if you remember, when you have a power to a power, you actually multiply those out. So this is equal to 2 minus x to the 1/4 power, which I'm going to take back into a root form, which would be the 4th root of 2 minus x. Okay, so now let's think this through. Okay, so this is my solution for the composite, but what about the domain? Okay, so let's recall what we said. The domain of this is going to depend on what the domain of the function on the inside was. So let's first look at this, and g of x is negative infinity to 2. Okay, so negative infinity 2. That means that on our composite function, even though we may have a different domain, we can only use these values on that new generated function, because this function right here would not exist without this one. So if this one's already restricted, we have to take that into consideration. Okay, so let's talk this through. What does the graph of the 4th root of 2 minus x look like? Okay, so I know a lot of you guys probably don't have that one memorized per se. As one of your parent functions. So I'm going to go ahead and use the calculator to show you so that you are convinced of to what this looks like. So let's go ahead and clear that out. So I'm going to say the 4th root. So I'm going to say math. The 5th option in my calculator allows me to put a different root. So I'm going to have the 4th root of 2 minus x. And well, actually, let's go ahead and just do the parent function first. My apologies. So just x. And let's see what this looks like. And as you can see, it looks not exactly the same as the square root, but very similar. So that should tell you then that the domain is also from 0 to infinity, which then means that to find the domain for this function, we would have to say 2 minus x has to be greater than or equal to 0. Therefore, 2 has to be greater than or equal to x, which then means at this point is that the domain of the composite function is the following: negative infinity to 2. However, before you kind of call it quits and say that's the domain, I'm going to compare that to what g of x is. Remember, g of x restricts this. So you need to ask yourself, is there any values from here that wouldn't work here? And the answer would be no, because it happens to be the same. Therefore, this g of x function really did not make any changes to the composite function itself. The domain didn't restrict anything, so that's why the domain is ending up to be the exact same thing. Okay, so what I'll do is to close out this video, well, not close out the video, but at least close out these examples. I want you to try using the same functions. Now do g of f of x. Okay, I'm assuming you gave it a go. So here's what I came up with, so let's talk about it. So g of f of x, remember I'm going to go ahead and use parentheses, help myself out. Everywhere I see an x, and inside of that I'm going to plug in f of x. So in this one it happens to be 2 minus the square root of x. Algebraically, there's really not much I can do to clean this up, so I'm going to leave it like that. That would be your composite function. So now let's find out what the domain is. Little reminder is, because we are plugging in root x, if we're gonna find its domain, we gotta first kind of find out the domain of that. So the domain of that is 0 to infinity. So this is gonna restrict our final answer. So we gotta keep that in mind. Okay. So now here's our final answer. Remember that to find the domain of a square root function, the inside of it has to be greater than or equal to 0. So that's what I did. I'm solving for x, so I'm gonna go ahead and add the square root of x to this side, which gives you 2 is greater than or equal to root x. I'm going to square both sides, which means that 4 is greater than or equal to x, which is the same thing as saying from negative infinity to 4. However, that's what the domain would be if this was what you were originally given. But this does not work, or this does not exist without having previously done this step. And because this step restricts your domain from 0 to infinity, we have to use this to restrict our final domain. So even though the domain of this entire thing is negative infinity to 4, this has to be restricting that. So as you can see, according to this domain could never have any negative numbers, so that's gone. So technically I can start at 0 and go to infinity. So if I compare that, this one doesn't go to infinity, but I can definitely start at 0 and end at 4. Therefore, the domain of the final solution should be from 0 to 4. Okay? All right. Hopefully, as you can see, maybe finding the domains can be a little bit challenging for some of this. However, finding the actual composition is not too terrible. Okay, the last example that we're going to talk about is actually to do the opposite, to decompose, to break apart. So let's kind of talk about what that means. So let's pretend that you have a function. So let h of x equal f of g of x. So in other words, we have a function. So in other words, like we have already the result. And that result is made up of the combination of two functions, or the composite function. Okay, so what we're going to do is that we can find those two functions separately, and then if we do the composite function, is going to give us back that original. So in other words, guys, it looks complicated, but really what I'm trying to say is, if I give you a final function, can you break it apart into two separate ones? Okay, so let's do an example. Let h of x equals f of g of x, and let's say that h of x is equal to 1 over x squared plus 1. Your job would be to find what f of x is and what g of x is. All right, so what I typically do is, by the way, there's multiple answers. What I encourage my students to do is use the same trick I kind of use with the parentheses to help you out. Now, when there's no parentheses, what I recommend is that you can throw parentheses somewhere in here to help you out. So for example, I'm going to go ahead and do one example with you to see what I mean. So let's say I throw parentheses in there. So inside the parentheses is an x squared. So inside the parentheses, it's the g of x. So what I'm going to say is that g of x is equal to x squared. Now I'm going to pretend that x squared is gone. So technically I am left with 1 over parentheses plus 1. Remember, when we were doing composition, the parentheses represent an x. So what I'm going to say then is that f of x is equal to 1 over x plus 1. Now notice, if I do the combination of the two, where I do f of g of x, I would put parentheses here, and inside those parentheses I would put the g of x, and that would give me back that answer. Cool? So that could be an answer. That is a decomposition of that. That is successful, and that would be correct. But let's say maybe somebody else saw something differently. For example, let's say your partner that you're working with maybe said, hey, I'm going to throw my parentheses in here. So then their answer is going to say, okay, g of x is equal to x squared plus 1. And that would technically leave you with 1 over parentheses, which 1 over parentheses, we will replace the parentheses with an x, and that would give us 1 over x. And if I do the composition of those two, I will still get the same answer. And this is also correct. And then this one is technically correct, but typically I don't accept this, but I have seen this before. Someone in the past have done this where they're like, okay, I'm going to throw a parenthesis in here. So they're like, okay, so g of x is equal to 1 over x squared plus 1, which then means that f of x would be whatever's left over, which in that case is just parentheses, which is x. And I'm like, well, I mean, technically you are correct. If I do the composition of this two, if I plug this into there, I'm going to get back that answer, which you are not wrong, but come on. That's really not creative. You can do this for everything. You can just let one of them be x all the time, and you don't really have to think about it. So I'm not going to accept this as the answer, but I mean, technically you can do it, okay? But really my point here, guys, is that you can get multiple answers, okay? The important idea here is, can you decompose? Can you at least see one of the answers, okay? The reason why this skill is going to be so important for you is that in calculus you're going to learn something known as the chain rule, which requires you to be capable of seeing a function and breaking it apart into maybe 2 or even 3 functions. Okay, all right, other than that, to not make this video any longer, I think that the one example, it's kind of self-explanatory. You'll have some practice on your homework. So thank you for watching this video, and we'll see you next time.